Hi everybody, in this video I'm going to go over APEX section 10.1.1, which is an introduction to waves. So first of all, we want to know what is a wave. Well, a wave is a disturbance that carries energy through space. Okay, so waves carry energy, not matter. That is a distinction there. So when we're thinking about waves, I like to think of a ripple, right? If you had a ripple of water, if you have all these water molecules on your surface of your water, and then you push down on one of them, this one's going to start wiggling, right? That's going to bump into this one, so this one's going to start wiggling. That's going to bump into this one, so then this one's going to start wiggling. And that is how your wave is going to propagate, right? Each particle is affecting the next particle and making it vibrate, okay? When we have this kind of wave behavior, we call this a mechanical wave. And a mechanical wave is a wave that requires a medium. So this medium could be any type of matter. It could be a solid, it could be a liquid, it could be a gas, right? So an example would be, in our ripple example, that would be a liquid medium. All the water particles were bumping into each other and propagating that wave, making that wave move. If you are talking, you're producing a sound wave, and so you're vibrating an air particle, which vibrates another air particle, and that makes your wave propagate, okay? So that is a mechanical wave that requires a gaseous medium. Another thing you might have is a solid medium. So if you had a younger brother or sister and they were having a tantrum and they stamped their foot on the ground and that might cause something on your table to shake, that is a mechanical wave that propagated through a solid medium, right? That vibration from the floor vibrated up through the table, okay? So these are examples of mechanical waves, and a lot of the waves that we're going to interact with are mechanical waves. There's also electromagnetic waves, which we've talked about a little bit before. We also call these light waves. And light waves are very special in that they do not require a medium. Okay, so what that means is they don't need particles to be vibrating and bumping into each other. They don't need any matter to move through. So if you think about light coming from the sun, right? Electromagnetic light comes from the sun and has to travel through space to get to us on Earth. Now, there's nothing in between us. There isn't air out in space. There isn't anything, any particles there that can vibrate. But still, the electromagnetic wave can travel because it does not need a medium. It is an electromagnetic wave. We talked about how that means there are an electric field and a magnetic field that are oscillating in opposite directions. And because of that, it does not require a medium. So these are a little bit more complicated, but the idea here is that a mechanical wave is a wave that requires some sort of particles to vibrate against each other, solid, liquid, or gas. And an electromagnetic wave does not require a medium. It does not require any particles to be there. Okay? All right. So there are a couple different types of waves. So let's start looking at some examples here. If we look here, I have an image of two types of waves. These are waves made by a slinky. A slinky is a really good demonstration of this. And you can see the top one is called a transverse wave. And in this, our pulse, our little wave, is making all the slinky rings move up and down as it travels to the right. The longitudinal wave is making a pulse also move to the right, but it's making all of the slinky coils sort of bunch up together. Okay, so there are two types of waves we're going to talk about the most, transverse and longitudinal. So let's look at this a little more closely. Let's first take a look at longitudinal waves. So this is a graphic of a longitudinal wave. and you can see that the wave is moving to the right. And it's causing the particles to sort of bunch up and then separate, right? But if we look at our one little red particle here, you can see that the particle is not moving all the way to the right. When you first see a wave, it sort of looks like all the particles are just moving in one straight line to the right. But we look individually, you see that that's not true. That our particle is just sort of moving left and right, okay? So our particle motion is this way. Okay? But we notice that it's not traveling the whole length of the wave, it's sort of staying in one area. That's important. So something that separates longitudinal waves from transverse waves is that longitudinal waves, the particle motion is in the same direction as the wave motion. Okay? So let's write that down. Particle motion is in the same direction as wave motion. Okay? And longitudinal waves sort of look like you have a whole bunch of things bunched up, and then those particles are sort of spread out, and then it's bunched up again, and then it's spread out again. Okay? And when we have this, these areas of bunched up are called compressions. And the areas where the particles are more spaced out are called rarefactions. Okay? So a common example of a longitudinal wave would be a sound wave. So let's take a look at what a sound wave looks like. So if we look here, we have a loudspeaker that is producing a sound wave. And you can see that all these particles sort of bunch up together, and that bunched up wave moves to the right. But again, if you look at that one red particle, it's not moving with the wave. It's just oscillating back and forth. So when you have sound, you have a bunch of air particles that bunch up together and then they move, right? So that's what a sound wave looks like. It is an example of a longitudinal wave. Now let's look at some transverse waves. Okay. All right. Here we have our transverse wave. And we can see again, our wave is moving to the right. And if we look at our red particle here, we can see it's moving up and down. So again, when you first look at a wave, you would think that the particles are moving up and down with the wave to the right. But if you actually look at each individual particle, you see that it's staying still, it's just moving up and down. It's not moving with the wave. And one property of transverse waves that's different from longitudinal waves is that the particle motion is going to be perpendicular to the wave motion. So the particle is moving up and down, but the wave is moving to the right. So let's write that down. Okay, our particle motion is in the perpendicular, remember that means 90 degrees, direction as wave motion. Okay, so our transverse waves look something like this. Okay, this is what you've seen in like a sine wave from math class. So an example of a transverse wave would be an electromagnetic or light wave. So let's look at an example of that. You can see that either in the blue and red or the brownish color, you see that it is oscillating in this transverse wave direction. So this is what an electromagnetic wave looks like. We've shown this once before. Okay? So again, we have two types of waves. We have longitudinal and transverse waves, and we need to know the difference between them. Okay. Now, all waves have a set of properties. I want to go through those now. So the first property is amplitude. The symbol for amplitude is A, and the unit is a unit of length. So it's usually meters, but it could be nanometers or kilometers. What amplitude is, it's the maximum displacement of a particle from its resting position as a wave passes. So if I draw a wave, I'm just going to do a transverse wave because it's a little easier to see, but it's the same idea for a longitudinal wave. Oops. This would be our amplitude. Okay, so if we look at our example, going back to this, okay, the amplitude is how much this particle moves up and down, how far this moves from its resting position. That's the amplitude. The next property I want to talk about is wavelength. Wavelength, the symbol is lambda. This is a Greek letter. How we draw it is we kind of start at the top, we make a little line looping down, and then one to the side. That's a lambda. Okay, and it's measured also in length, so usually meters, but it could be nanometers or kilometers. And it's the distance between any two adjacent crests or troughs in a wave. So let's look at another wave here. Okay, if this was our wave, this top part is called the crest. The bottom part is called the trough. And the distance between two adjacent crests or troughs is our wavelength. Okay, that's our wavelength. All right, next is period. Period, the symbol is T, capital T, and the unit is seconds. What a period is it's the time it takes for one complete wave to pass a point. So if we have a wave, the time for it to go for one complete wave like this through one single point, right, this would move, is the period. The frequency is, the symbol is F, lowercase f, and the unit is hertz. 1 hertz is measured as 1 divided by seconds, and we're going to talk about that more in just a minute. Okay, what the frequency is it's the number of complete waves that pass a given point in a second. So a high frequency wave looks like this, okay, where a lot of complete waves pass in a given second. Low frequency would be something like this, where not too many waves pass in a given second. Okay, next is wave speed. Speed, just like always, uses the symbol V, and the unit is meters per second, and it's just how fast the wave is moving. It's pretty self-explanatory. The next is wave energy. Energy is abbreviated with an E, and it's measured in joules. J is for joules. Okay, and this is the wave's ability to do work. So these are the 6 properties of waves that I would like you to be aware of. We can also do a little bit of math involving waves. So first I want to talk about frequency. So period and frequency are inverse relationships, okay? So the period is equal to 1 over the frequency, and the frequency is equal to 1 over the period, okay? So for example, if a wave has a period of 6 seconds and I want to try to find the frequency, I can use this equation. Okay, so I would use frequency equals 1 over period, 1 over 6 seconds, and I would end up getting 0.17 hertz. And again, hertz is a 1 over second. That's what the unit means, okay? And what this number means, what this means here, is that there's one wave every 6 seconds. Okay, so we can perform some calculations involving period and frequency because they are inverse relationships. Now, there's also a relationship between velocity, frequency, and wavelength. Okay, so our velocity equals our frequency times lambda, our wavelength. Okay, so for example, let's say we have a 40 hertz wave with a wavelength of 1.5 meters. Okay, now we can plug into this equation to find the velocity. Velocity equals our frequency, which is this, 40 hertz, times our wavelength, which is this, 1.5 meters, and we would get 60 meters per second. Okay? Remember, hertz is per second. That's how we get meters per second. So this is pretty simple. You can also move around this equation to find other equations. So we have this equation here, but we can also manipulate it to get other equations. So let's say if we want to try and get, if we have V equals F lambda and we're trying to get F by itself, we can divide by lambda. And now we get a new equation. We get F equals V over lambda. Okay. You can also get one more equation. Let's start with our same one. Oops. Let's say we want to get lambda by itself, so we divide both sides by F, and we end up with lambda equals V over F. So we actually have 3 equations here. Let me write them out for you. We have V equals F times lambda. We have F equals V over lambda, and we have lambda equals V over F. So these are all equations we can use to relate these different quantities. So let's do one more example with this. So let's say we have a wave traveling at 250 meters per second, has a wavelength of 2 meters. Okay, so let's look at what we have here. This has to be our velocity. This is our wavelength. So what are we missing? Frequency. So that means I'm going to use this equation here. So I'm going to use frequency equals V over lambda equals 250 meters per second divided by 2 meters, and I get a frequency of 125 hertz. That would be my final answer. So these equations are pretty simple, but the thing to know is that we started with that first equation and then we derived the other 2 from it. Okay, so for waves so far, what we want to know is the difference between longitudinal and transverse waves. We want to know these 6 properties of waves and how to do calculations involving these equations. Thank you.